Hello, everyone. Welcome back. Okay, this is video 2 for week 2. Okay, in this video, we're going to take a look at a bunch of stats concepts. Okay, so all of you have had a stats class either on campus here or perhaps at your community college. So some of these things are going to look familiar, I hope, and then some of these things are going to be probably new because they would have extended beyond your sort of core lower division stats class that you've probably had. Okay, but one of the things that we have to do here is to run through some statistical ideas because when we do testing, we generate lots and lots and lots of numbers. And we have to have some way of summarizing those numbers and describing those numbers. Otherwise, we would just be overwhelmed by the sheer number of numbers that we get. So in this video, we'll end up talking about things like percentile ranks, standardized scores, confidence intervals, standard error of measurement, etc. And these are all things that are going to come back up as we start talking about testing, okay, as we move through the quarter and so on. Okay, so let's start, okay, with just a set of numbers. Okay, let's just assume that we have a set of numbers like these numbers here. Okay, these numbers could just come from some tests that we've administered, and we just have a bunch of scores. Okay, well, if you looked at this set of scores, you would eventually figure out what the lowest score is, what the highest score it was. You'd figure out how many of each of the scores there were. You'd figure out if there were some scores that just didn't happen, you know, that would have fallen in the range from lowest to highest. But it would take you a little bit of time to answer those questions. So the idea behind the statistics concepts that we'll focus on is how do we take a group of numbers like this and make them easier to understand, make them more meaningful? Okay, so instead of looking at a set of numbers like you see on the PowerPoint here, we could take these numbers and put them into a table. Okay, so one way to describe data is with a table. And one kind of table is this thing called a frequency distribution. Okay? A frequency distribution is simply a table that identifies all the possible scores and the frequency with which each of the scores happen to occur. So if we were looking at that data set that I showed you in the previous slide, we would see that the lowest score was a 21, the highest score was a 28, and so we just list in the column that's labeled score, or if we actually, instead of having a generic set of data, if we had IQ scores, we could call that the IQ score column. But we would just list the scores from lowest to highest. So in this case, 21 to 28. Then we could look at the set of data that I showed you in the previous slide, and we would count up the number of 21s, the number of 22s, the number of 23s, the number of 24s, and so on. And we would put that number under the heading that says F. And F stands for frequency. So this means there were 2 21s, 5 22s, 0 23s, 12 24s, 7 25s, 3 26s, 0 27s, and 5 28s. And if you were to go back to the previous slide and actually count up how many 21 through 28s there were, the numbers in the column labeled F should correspond to what you counted up. But as you can tell, in using this table, it is much easier now to figure out what was the lowest score, what was the highest score, which score had the most number of occurrences, which scores were not even in the set of scores. If I were to ask you those questions and you were to use this table, you could easily find answers to those questions. So for example, if I said, what score happened the most? You could easily look at that column labeled F and go, oh, there's a 12 there. And the score that's associated with the 12 is a 24. So the score of 24 happened the most. If I were to ask you, were there any scores between 21 and 28 that didn't occur? You could say, yes, 23 didn't occur. 27 didn't occur. Okay? So what this table has done for us is to take a set of data which isn't easy to figure out, for example, this set of data, and we just took it and put it into this table, and now all of a sudden everything makes sense and it works in terms of being able to very quickly figure out, okay, what the set of data looks like. Okay, so a frequency distribution is one way to describe a set of data. Okay, the frequency distribution has a close relative. It's called the cumulative frequency distribution, and it looks a lot like the frequency distribution, except with an additional column that is labeled CF for cumulative frequency. Okay, what the cumulative frequency does is that it tells you the number of scores that are at a particular value and less than that value. Okay, so if you look at this table here, it is based on the same data set that we started with. If you look at the first two columns labeled score and F, that is the frequency distribution that we just talked about. We're going to add a third column now called CF, cumulative frequency. Okay? And in this column, we're going to indicate the number of scores that are at that value and less than that value. So for example, if we look at the score 21, there are two 21s in the set of data that I showed you. There are no values less than 21. So therefore, the cumulative frequency at 21 is 2, because there are two scores at 21 or below. If you look at the score 22, we see that there are 5 22s in the set of data that I showed you. Therefore, there's a total of 7 scores at 22 or less. In other words, there's 5 22s, 2 21s. Therefore, there are 7 total scores at 22 or less. If you look at the score 23, 23 didn't happen. So there is still 7 total scores at 23 or less. If you look at the score 24, there were 12 of those scores. So therefore, the cumulative frequency at a score of 24 is 19, because if you add up the 12 plus the 5 plus the 2, you get 19. Okay, and so on until you get to the final score of 28. At 28, there are 34 total scores at 28 and below. And if you were to go back and count the numbers in the table or in the distribution of scores that I gave you at the very beginning, you should have 34 scores. Okay, so that's a cumulative frequency distribution. Now, what's important about this cumulative frequency distribution is that it starts giving you a sense of how the scores sort of lay out. Okay, so for example, we know that there's 34 total scores in this particular set of numbers. Okay, well, if I say, what score is about the halfway point? Okay, well, if there's 34 scores, half of that would be 17. So, the score that is about halfway through the scores is about a 23, 24, right? So now all of a sudden, it gives you some sense of how the scores distribute. So you know that about half of the scores are less than 24, about half of the scores are greater than 24. You could have eventually figured that out from the data set that I first gave you at the very beginning, but it would have taken you a long time to figure that out. But with a cumulative frequency distribution, it makes it pretty easy to figure out things like that. And that's, again, the whole idea here. We're using statistics to describe a large set of data in a way where it's easier for us to understand what the data happens to be. Okay, so that is our cumulative frequency distribution. Okay, it, along with the frequency distribution, represents how we can use tables to summarize a set of data. Okay, now sometimes we don't want to use tables to summarize a set of data. Okay, we want to instead use a number, one number, to describe an entire set of numbers or data. Well, if that's what we want to do, then what we're dealing with is this thing called measures of central tendency. Okay, measures of central tendency, of which there are multiple types, and we'll talk about them. Measures of central tendency is a kind of statistic where we try to use one number to describe an entire set of numbers. Okay? For the most part, we can do that. There's only one situation where we might violate this notion of using one number to describe a set of data. And we'll talk about that in just a second. But the general notion with any measure of central tendency is that we're going to use one number to describe an entire set of numbers. Okay? So one example of a measure of central tendency is this thing called a mode. A mode is simply the most frequently occurring number in a set of data. Okay? In other words, if you have a frequency distribution or a cumulative frequency distribution setup, you can look at either one of those tables, look in the column labeled F, and find the biggest number in that column, look over to the column that's labeled scores, and record the score associated with the biggest number in the frequency column. That is your mode. So for example, the mode in the sample data that I gave you is 24 because it happened the most often of any of the scores. Now, if for some reason there were two scores that were equally frequent, you would have to record both of those scores. If there were three scores that were equally frequent, you would have to report all three of the scores. So the mode is the one case where we're sort of violating this idea of using one number to describe an entire set of numbers. All right? Couple of things to keep in mind with respect to the use of the mode. Okay? The mode ignores the magnitude of individuals' numbers in the set of data. In other words, it doesn't care what the actual scores are. It's just looking for the score that happened the most frequently, and it's just reporting that score and using that number as a description of the whole set of scores. So it really doesn't matter, what the magnitudes of the individual numbers are. All that matters is how many times did the numbers happen, and I'm going to report the number that had the most frequent occurrence in the set of data. Okay, that's one thing to keep in mind. The second thing to keep in mind, okay, is that the mode can be incredibly unstable. Right? In other words, if I change just one number in the set of numbers, I could change the mode. Okay, and so in that sense, in using this one number to describe a set of data, it's not necessarily the greatest, okay, way of describing a set of numbers. So that's why we have other examples of measures of central tendency. We have this thing called the median. Okay, the median is the middle number in a distribution of numbers, and we use the number that's right in the middle to describe the whole set of data. Okay, so what happens here, okay, is that you have to take the set of numbers that you're working with, and you have to put them in order from lowest to highest. Once you have them in order from lowest to highest, you then work from not either, but both ends. And you chop off a number from both ends, and you keep doing so as you move towards the middle. And when you get to the middle, that is the median. Now, if there is an unequal number of scores, okay, in other words, an odd number of scores, if you were to work from both ends and chop off a score coming to the middle, you will end up with one score in the middle. That's your median. If there's an even number of values and you chop off a score starting from both ends until you get to the middle, you're going to end up with two scores in the middle. But again, remember, measures of central tendency are based on the assumption that we're going to use one value to describe a set of values. So since you have two numbers in the middle, you can't really report both. So what you do is you just find the average of those two numbers in the middle and you report that. So in our case, with the set of data that we started with, the median for the sample scores is 24. Okay. Now, the thing to keep in mind with the median, okay, is that it ignores every score except for what's in the middle. So it doesn't matter what the scores are to either side of the middle. The only score that's going to be used to describe the whole set of scores is whatever's in the middle. So in that sense, it might be sort of unrepresentative, because if you have some really low scores and you got some really high scores and you only report the middle score, that middle score doesn't really tell you that you got really low scores and really high scores. Okay, so in that sense, the median is a bit of a hiccup in terms of describing a set of scores. So we have this third measure of central tendency, which is one that you guys have been using forever and ever and ever. We have a formal name for it. It's called the mean, but really the mean is just the average, which you've calculated a million times in terms of thinking about your class performances and so on and so forth. The average is add up all your scores, divide by the number of scores you have. Now you have the average or the mean. So for our sample scores, the mean is 24.5. I just add up all the scores, divide by the total number of scores, and I should get a value of 24.5. Well, with the mean, I've accounted for every single score because I added up every single score, then divided by the total number of scores. So in that sense, this one score in this example where it's 24.5, that sort of is representative of all the individual scores, but I'm only reporting one number. Okay, so again, remember, with our measures of central tendency. The idea is we're going to describe a set of scores using one number. In the case of a mode, we're going to use the most frequently occurring number to describe the set. In the case of the median, we're going to use the middle number in the distribution of scores that is ordered from lowest to highest to represent the whole set of scores. And in the mean, or the average, we're simply going to add up all the scores, divide by the total number of scores, and use that value to describe the whole set of scores. Okay, so the mode, the median, and the mean are our three measures of central tendency. So far, we have tables, the frequency distribution and the cumulative frequency distribution, and we have the measures of central tendency, the mode, the median, and the mean as ways to describe numbers, to describe performance. Okay? Now, we have other ways of describing numbers and performance. Okay? What we're going to cover now are those things that are going to be especially important in terms of the testing that we'll be talking about throughout the rest of the quarter. Okay, so these are still statistics, okay, but they are especially pertinent, okay, to the things that we'll be talking about after this week. Okay, so we start with this thing called the percentile rank. The percentile rank has to do with taking a score and transforming it into a new value that tells us where this score lies. And it tells us that information in terms of the percentage of people who are at that score and below it. So by default, you know the total number of people must be 100%. So you know the percentage of scores above this particular value. Okay? So in other words, when we're using percentile ranks, we're trying to describe a particular score, not a whole set of scores, but a particular score. Okay, so to calculate a percentile rank, we need two steps. The first step is to construct a cumulative frequency distribution. Well, we've talked about that already. Okay, that was one of those table, okay, tabular ways of describing data that we started with. Okay, so we first need to have a cumulative frequency distribution. Then, for step two, we're going to calculate the percentile rank using the formula that you see here. Percentile rank equals CF for the score of interest divided by N times 100. Okay, so let's practice this. Let's say that we have some student heights. Okay, so let's just say that we took some students and we measured their heights. Okay, I don't know, a bunch of elementary school kids or something. And we took these kids and measured how tall each one is and recorded, okay, the heights for each of these students. Okay, and let's say that what I have is a set of students whose heights went from 60 inches to 68 inches. And you can see that there was one kid that was 60 inches tall, 0 kids that was 61 inches tall, 1 kid 62 inches, and so on, all the way to 68 inches. Okay, so what I'm showing you here, okay, in this slide is the frequency distribution. You see the third column there that says CF, okay? That's the cumulative frequency distribution, which I have not done for you. So I want you, okay, to do the cumulative frequency distribution column. Okay, again, remember, the cumulative frequency is going to be the total number of, in this case, heights that are at a specific height and below it. So I'll start you out, you finish it. So the cumulative frequency at 60 inches is going to be 1, because there is one kid who is 60 inches tall. No one is less than 60 inches tall, so the cumulative frequency is 1. The cumulative frequency at 61 inches is 1, because there's 0 kids who are 61 inches. There's 1 kid who is 60 inches. So the cumulative frequency is 1, because there is 1 total kid that is at 61 inches or less. At 62 inches, the cumulative frequency will be 2, because there's 1 kid who is 62 inches, 0 at 61 inches, 1 at 60 inches. So there is a total of 2 kids at 62 inches or shorter. Okay, you finish the remainder of the cumulative frequency column. Okay, now, given that you have the cumulative frequency column, we are going to find the percentile rank for a height of 65 inches. Okay, so you go ahead and do that using the formula on the previous slide and the directions on the previous slide. You do that, work it out first, because the next slide is going to show the answer. Okay, here we go. A height of 65 inches is at the 67th percentile rank. Okay, so when you did your calculations according to the formula that I gave you, you should have gotten the number 67. Okay, and we would simply say it's the 67th PR, or percentile rank. In other words, this is saying that 67% of heights in this set of heights is 65 inches or shorter. Therefore, 33% of heights are taller than 65 inches, because the total percent of heights must equal 100%. Right? The importance of the percentile rank is that it tells us about relative standing. In other words, it tells us where a number falls relative to other numbers. Okay? In this case, the 67th percentile rank tells us the height of 65 inches is above average, because the 50th percentile is average. Okay, because remember, there's a total of 100% possible, right? Well, if you chop 100% right in half, that would be 50%. 50% is the 50th percentile rank, and we give it a qualitative name called average. So in this case, we can say that a kid with a height of 65 inches is above average. Right? We can also say if some kid has a height that is at the 30th percentile rank, that 30% of heights are at that height and below, which means 70% of heights are above that height. So therefore, that kid is below average. Okay? Now, this notion of relative standing becomes very, very, very important for us, okay, as we move more and more towards testing and this idea of making diagnoses and so on. Okay, so we're going to come back to it, okay, over and over and over. Okay, but for now, what's critical to understand is what a percentile is. It tells you the percentage of scores that are at a particular value and less than that value. By default, you know the percentage of scores above that value because the total must be 100%. Okay? Now, it is absolutely critical to keep in mind that a percentile rank is not percentage correct. In other words, if we say that some score is at the 80th percentile rank, it does not mean that that person got 80% correct. Okay? The 80th percentile rank is saying that that person's score is such that 80% of scores are at that person's score and less. 20% of scores are above this person's score. So therefore, this person has done quite well, quite above average. 80% is, 80% correct is, hey, there were a certain number of items or a certain number of points that you could get, and you got 80% of those points. Says nothing about how many scores, what percentage of scores is at a particular value and less. Okay, so it is absolutely critical that you keep percentile rank separate from percentage correct. Okay, so these percentile ranks represents another way to describe numbers or performance. Okay, now we have yet another way to describe numbers or performance. These things are called standardized scores. Okay, standardized scores are just statistical mechanisms, statistical processes by which we can give more meaning to some number. Okay, so let's just say that we have a score of 41. Okay, if you just saw that score of 41, you really don't know what that score means. Okay, because it's just a number. You have no context around that number. If I were to tell you that the number of possible points is 1,000 and somebody got a score of 41, you'd say, wow, that person didn't do so well. If I instead said, well, the number of points possible was 42 and some score was 41, you'd say, wow, that's a really good score. But because there's no context right now, we don't know what this score means. It's just a number. Okay, so what we need is something to make that 41 more meaningful. This is where standardized scores come into play. Standardized scores help us to give meaning, to make sense of numbers, so that we're not just looking at the number going, well, I don't know, it's just a number. Okay, so one kind of standardized score is this thing called a z-score. Okay, a z-score is just a way to transform a number, for example, the 41 that I showed you in the last slide. It's a way to transform that 41 into a new value that shows us how far above or below the mean the score falls. Okay, so in other words, instead of just looking at that 41 and going, well, I have no idea what that means. What a z-score does for us is to take that 41 and make it into a new number. The new number tells us how far above the mean or below the mean the score happens to fall. Now we have meaningful information because we can say, oh, the 41 is above average, the 41 is below average, or the 41 is right at average. If we didn't have the z-scores, we would just have this 41, but we wouldn't be able to do anything with it in terms of giving it meaning. Okay, so let's just say that we have two scores. Okay, this could be scores from test A and test B, or it could be scores from person 1 and person 2. So we have a score of 52 and a score of 105. If I were to ask you, which of these two scores, 52 or 105? If I were to ask you, which has the stronger performance? It would be hard to know because there's no context for the 52. And there's no context for the 105. But if I told you that the mean for test A or person 1 was 50 and the standard deviation was 2, and if I said the mean for test B or person 2 was 105 and the standard deviation is 2.6, you could calculate a z-score, this thing here. You could calculate a z-score for person 1 or test 1, then calculate a z-score for person 2 or test 2, and you would have now two scores that you could put on a graph that looks like this, where, see right in the middle, you have a z-score of 0. Then to the right, you have +1, +2, +3. To the left, you have -1, -2, -3. Well, when you calculate the z-score using this formula here, you're going to get a value that is between -3 and +3. So if you use these numbers and calculate the z-score for test A or person 1, calculate the z-score for test B or person 2, you can now locate where each of those z-scores falls. And you will then know which score is higher or lower relative to the other. Okay, so go ahead and do that before you go on to the next slide. Now, assuming that you've calculated the z-score and there are no questions, and if there are questions, make sure you write them down so that when we meet up, we can address those questions. Okay? I'm going to show you some other standardized scores here. Okay? We're not going to have to calculate these like we did with the z-score. I'm just going to give you, in this case, the core characteristics of 3 kinds of standardized scores that we're going to use over and over and over when we do testing. You're going to want to memorize these characteristics for each of these standardized scores because you're going to need to be fluent in these characteristics so that when we get to actual testing stuff, you don't get bogged down trying to figure out what the testing numbers are saying. So we have t-scores, scaled scores, standard scores. I show you the range for each of the scores. I show you the mean for each of the scores and the standard deviation for each of the scores. Okay. Again, what you're going to want to do is to memorize, okay, the characteristics for each of these standardized scores. Right? And you're going to want to get really, really fluent with these scores. Okay. Now, besides our tables, besides the percentile rank, besides the standardized scores, we want to talk some more about other statistical ideas that we're going to really, really, really need when we get into testing. Okay? Before we do that, we want to talk about why these standardized scores are so, so, so important. Okay? When we do evaluations of children, okay, for the purposes of trying to make a diagnosis of some learning related concern, we are making that diagnosis in a norm referenced manner. In other words, when we make a determination of whether a kiddo has an educational concern or not, we are doing so by saying, this kid is demonstrating these kinds of weaknesses. Are those weaknesses different than other kids, typical kids? If so, the differences are enough to say the kid should receive some kind of diagnosis. If, on the other hand, we say the differences are not different enough than typical kids, this kiddo will not receive a diagnosis. So in essence, in norm reference measurement, what we're doing is saying typical kids are the norm. If the kid that we're testing and evaluating is like the norm, the kid has no diagnosable condition. If, on the other hand, the kid is different than the norm, there's a basis for saying that the kid should receive a diagnosis. That's how this notion of relative standing plays a role. Because when we're comparing a kid to the norm, we are in essence determining the kid's relative standing compared to the norm group. That is norm referenced measurement. Criterion reference measurement is not used when we do psychoeducational evaluations. It's used when you think about all the midterms and final exams you've ever had, both in K through 12 and in college. Criterion reference measurement has to do with how much of a criterion did you get? That determines how well you've done. So for example, if a test has 100 points possible, that's the criterion, 100 points, and you get 95 of those points, you have done incredibly well because you got 95 out of the possible 100. On the other hand, if you have that test that has 100 points and you get, let's just say, 35 points, you would know for yourself, based on all your experiences with tests, you really didn't do that well because the criterion, the points possible, is 100. You got 35. That's a very, 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 very small chunk of the 100. Therefore, we know your performance was not very good. But you see how in criterion reference measurement, we're not comparing you to the norm. We're comparing you to a criterion. Again, when we do educational evaluations of children, we're never using criterion reference measurement. We're using norm reference measurement, where we're interested in relative standing. Now, the other reason why these standardized scores are important is because if everything is put on the same scale, we can sit there and, in quotes, compare scores from different measures, okay? Because everything will be on the same scale. Okay? Now, that's not going to make a whole lot of sense yet, but just hang on to that thought because it'll make sense as we go through the rest of the quarter. Okay, so again, besides our standardized scores, we have other important stats ideas that we have to throw in here and that we have to get you comfortable with. Okay, so what we have here, okay, is the notion of standard error of measurement, which is then going to get tied to the notion of confidence intervals. Okay, standard error of measurement has to do with the standard deviation of scores generated by testing and retesting individuals. Okay, now that's a formal definition. I'll give you an informal explanation. Just pretend that we are going to take a group of people and we're going to give them, we're going to administer them some test multiple times. If every individual was given some test multiple times, it is very, 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 very likely that for any one individual, that his or her score would not be the same on each of the administrations. Okay? In other words, if I were to give you an IQ test 3 times, your score would probably not be identical across those 3 administrations. We would hope that they're very, very similar, but they're probably not identical. The same thing would be true if I did the same thing with another student in class. And the same thing would be true if I did the same thing with a 3rd student in class, with a 4th student, with a 5th student, with a 6th student. There's always going to be some difference in the scores between the first administration, the second administration, the third administration. Doesn't matter how many administrations we do. How much the scores spread out per person, averaged across all the people that were tested and retested, is the standard error of measurement. So if you're thinking about the quality of a test, you would want the standard error of measurement for some tests to be as small as possible. In other words, the scores don't spread out much when we test and retest people. So therefore, the standard error of measurement is going to affect our estimate of the individual's true score. In other words, if a test has a very low standard of error of measurement, when we give it the one time that we give it, we're going to get a good approximation of the person's true score. On the other hand, if some test has a high standard error of measurement, when we give it the one time in real life, we're probably not getting as good of an indicator of the person's true score. The reality is there is no test that has a standard error of measurement that is 0, which is of course what we would want. So given that every test has some amount of error, we just want it to be as small as possible. But given that every test has some amount of error, what we have to do is to create these things called confidence intervals. Okay? Confidence intervals tell us where the person's true score is likely to fall given what their score on the test is today. Again, knowing that the score on the test today is not, in all likelihood, going to be 100% on point. So given that it's not 100% on point, we want to know what range is this person's true score likely to fall in. So just think of it this way. The smaller the standard error of measurement, the smaller the confidence interval. The bigger the SEM, the bigger the confidence interval. In other words, if there is very little error in the test, I'm going to need a smaller range of scores in which I'm likely to find the person's true score. If, on the other hand, I have a lot of SEM, I'm going to need a much broader range of scores in order to capture the person's true score. So what I have to show you now is how we would calculate a confidence interval. There are 3 confidence intervals that we can calculate: a 68%, 95%, and 99% confidence interval, or CI. The 68, 95, and 99 basically represents the degree of sureness that you're comfortable with. Okay? In other words, we can be 68% sure that a person's score is going to fall in a certain range. Or we can be 95% sure that a person's score is going to fall in a certain range. Or we can be 99% sure that a person's score is going to fall in a certain range. Now, for evaluation purposes, it doesn't even make sense to say, oh, I want to be 68% sure. Because who would want to go, let's make decisions when we're only 68% sure? No, doesn't happen. Even though we don't see it often, it is one of the confidence intervals that we can calculate, so I show it to you here. For our purposes, when we're talking about testing and evaluating kids, we want to be as sure as possible. So we're either going to use the 95% confidence interval or the 99% confidence interval because it makes sense to say, I'm 95% sure that given your kid's performance today, that his or her real performance is going to fall between this score and that score. Or I am 99% sure that given your kid's performance on this test today, I am 99% sure that his real score or her real score will fall between this value and that value. That sounds right, but it doesn't sound right to say, oh, I'm 68% sure. Regardless, confidence intervals are impacted by the standard error. The bigger the standard error, the bigger the confidence interval. The smaller the standard error, the smaller the confidence interval. Okay, so calculating confidence intervals is actually pretty straightforward because all we have to do is to take the person's observed score, in other words, the score that we have for the person today, we're going to add and we're going to subtract a certain amount of the standard error of measurement. So for example, with a 68% confidence interval, we're going to take the observed score, add and subtract 1 SEM. For the 95% confidence interval, we're going to take the person's score, add and subtract 2 SEMs. For the 99% confidence interval, we're going to take the person's score, add and subtract 3 SEMs. Okay, so here's an example. Let's say that we have a person who has a score of 105. And we know that the SEM for this test is 4. And we know the standard deviation is 3.1. The standard deviation, or S, is irrelevant here because the formula is observed score plus or minus some amount of SEM. So for example, for the 68 percentile, 68% confidence interval, not percentile, we're going to take the observed score and we're going to add and subtract 1 SEM. So it's going to be 105 plus 4, 105 minus 4. Therefore, 101 to 109. In other words, based on this person's score of 105 today, I am 68% sure that this person's real score is between 101 and 109. I've given you the confidence intervals for 95% and 99%. You go ahead and do those calculations and make sure that you get the same scores as I have there. Okay, the same range of scores as I have there. This is the notion of a confidence interval. Again, it's based on this idea that when we give a test to someone on a certain day, we can never, ever, ever be sure that that particular score is 100% his or her real score. So therefore, we need this confidence interval. Okay. Now, we've covered a lot. All right. When we get together, I will find out from you if there are questions, and we'll try to figure out those questions in person. Okay. But hopefully, for now, this at least is making some sense. As always, as you go through this content, write down your questions, and then we'll work with your questions when we're live. Okay, that's it for now.